But DFA is by assumption a linear transformation. Remember, linear transformation of 0, 0. So yes, this eta sub f has to be a continuous function with limit 0. All right, so that's the backdrop. We'll use that language in the proof that follows. Yep.
Is it like continuous on 0? Or anywhere else?
Well, the different linear, what are we asking about? Eta.
Because you've only proved it continues at 0.
Yeah, I don't know about anywhere else, but I only care about 0 for this limit, so I don't know. I mean, I thought if you're asking me about the differential, good news, the differential is continuous everywhere. You guys proved that out. Thank you. Right, that was problem 3. Arbitrary linear map. Okay, anyway. So here we go. We have two functions, both differentiable at a, c a constant. Then the claim is that cf plus g is differentiable, and guess what? The differential of the sum is the sum of the differentials, and you can, just what you'd expect, all right? And the proof goes like this. So you have an eta sub f and you've got an eta sub g, right? And both of these quotients limit to 0, and my claim is that we can just use this as the differential of the sum, cf plus g. Now check this out. So eta cf plus g of h is then going to be equal to cf plus g times a of a plus h minus cf plus g at a minus the alleged differential, right? And when you work that out, you get c times this business and g, but that is by definition eta sub f of h times c and eta sub g of h. But these, right, why do I even need this? Like, I could just say, okay, so this goes to 0 because this goes to 0, that goes to 0, and we just proved that they both go to 0, right? Why am I doing this? I'm making life too hard. I don't need this. I have forgotten, apparently, that I proved this lemma up here, you know? My bad. So, you know, you don't need this. You could just go, this goes to 0 because we just proved that goes to 0, that goes to 0. So c times something that goes to 0 plus something else that goes to 0 goes to 0. Let's not make it more complicated than it needs to be, right? But if you want to, you could do this. So there's that one. Notice that if we put c equals to 1, we get additivity. And if we put g equals to 0, what was the differential of 0? 0. That's that constant thing we did earlier. Then we get, you can pull a constant out. So yay. Now, this is the chain rule. If we have two functions of norm linear spaces, and we can compose them if they're composable, then the Frechet derivative of their composite is the composite of the Frechet derivatives. Of course, the outside function has to be evaluated at the output of the inside function, and the inside function, of course, has to be evaluated at, you know. So this is the chain rule. All right. And I guess I have to look at the proof with you, but my heart is not in it. Because this one's hard. All right, so we'll do it. Okay, thank you, Preston. We'll get through it together. I like the spirit. Very good, very good. It's a new day. It's the glorious future is upon us and all that stuff. Let's see here. So, chickens. Oh, glorious chickens. No, I don't know. Okay. I'm not sure what that's about, but I'll allow it. So first of all, if we're assuming that g is differentiable at a, we can write the Frechet quotient like so, right? I mean, this isn't the Frechet quotient. This is the numerator of the Frechet quotient, right? Yeah. So we can write the numerator of the Frechet quotient for g like this, and we can write the numerator for the Frechet quotient of f like this, because f is differentiable at g of a, right? So instead of a, I have g of a here, and I'm using k because that's, you know, I wanted to use a different letter to distinguish the ideas here, so I did that. All right, so these are both linear the differentials are linear transformations, right? So one thing, when we compose linear transformations, good news, the composite of linear transformations is again a linear transformation. So we got that. The question then is, can we show that the, you know, the numerator of the difference quotient for the composite actually satisfies the needed limit, right? So then I work that out. So this is by definition all this jazz here, right? So that's what that means is f of g of a plus h, f of g of a, df of g sub a of dg of a of h. Why? Anyway, so this I can replace with, what's going on here? I'm taking the inside of this, right? And I'm unfolding it into I'm rewriting this in terms of the eta sub g, as I can do that. And over here, and this is just this again, so I just kept that the same, right? This stays the same. Let me scroll up a bit. Oh. All right, there we go. So we got to here, and then the next move I make here is to use the fact that f is differentiable at g of a to rewrite that as f of g of a plus the differential of f of g of a acting on this business here, which was dga of h plus a to g of h, like so. And then over here, what's this? Plus the eta sub f acting on the k, so to speak. This is the k. K is equal to d sub g of h plus eta g of h. This whole business here you can think of as the k that we had before. So eta f of k. And then I still have these two things which are subtracted down here. Boy. Now things cancel, right? The f of g of a cancels with the f of g of a. This is linear. So that means that this is this plus that, and then this piece and that piece, they'd be canceling, which just leaves us with the dga eta g of h like that, plus this eta f of dga h plus this eta g of h. All right. And then I decided to label this piece as quote unquote 1 and this piece as quote unquote 2 after division of this by norm h. All right, so first of all, number 1 we can understand using linearity and continuity of the map df g sub a, which is, okay, so I take this, what have I done? I've pulled the norm h inside, right? And then what do I do? I can do that because I'm assuming, well, this is linear, right? Then what? I pulled the limit. When can you pull a limit inside something? What's that using? That's using continuity. But we know that the linear map is continuous. Therefore, we can pull the limit inside a continuous map. So I can pull the limit inside by the continuity of the differential. But then that is a 0 by differentiability of g. So then we've got df ga of 0, which is equal to 0. Yay. All right. That's not bad. Now 2 is where I think there's a gap in my proof. So to get 2, it's not quite just eta sub f of k over norm k, since there's a norm h in the denominator. And my point is, if I could find like an m greater than 0 for which we had norm k is less than mh, then we could have this and this, and then I could squeeze this to 0 because I'm given that that's 0, which then would prove that 2 vanishes. But I don't. That's a gap in my proof at the moment. So I guess you guys work that out in homework. That is an empty threat. Relax. Let's see here. What's that?
Do you also need less than or equal to on there?
Less than or equal to.
You're going to call it?
I think not in this case because that limits to 0.
Oh, but it's always greater.
Yeah. So I think I could put less than or equal to 0. I think I could change both of those to not strict inequalities is what I'm trying to say. So, all right. Anyway, so I'm sorry to put you through that, but that's a sketch of the proof of the chain rule. All right. So we talked about the definition of directional derivative a bit, and I claimed this theorem that differentiability implies directional differentiability. Here's the proof of that. So suppose that you have f is differentiable. Then we know that this limit exists. All right? If that limit exists, that means that all path limits also exist. All right? So the path limit I can denote by tv goes to 0 as t greater than 0 of this. All right? But then I can pull out the norm of v like so, and then I have this equal to 0. And as absolute value t is equal to t for t greater than 0, I find that the limit as f of a plus tv minus f of a over t is equal to this limit, which is so basically I'm arguing this limit exists, right? So since it's that lemma again that I used earlier, since the difference, the limit of the difference is given to be 0, and we know that this piece of the limit is equal to 0, it follows that the other piece, the quote-unquote a in my lemma earlier, must also exist and be equal to the limit of b, which happens to be dfa of v here. And as such, but this right here is exactly the directional derivative. And I think what I have down here is, so I did it for t positive, then this down here is just the same argument, but for t negative, which introduces some minuses that are not interesting. But you get to the same place. So basically this gives us that the left and the right limits in the one-dimensional sense as t goes to 0 of the difference quotient is equal to the differential of a at v. But this by definition is the directional derivative of f in the v direction at a. And this proves then that if it's differentiable at a, the directional derivative exists and is also given by this lovely formula right here, which is super nice. The other direction, knowing that the directional derivatives exist, proving that it's differentiable, that's a more subtle business. We'll do that next time. But before today is done, I wanted to tell you something. So we did this example on the board already, okay? I'll talk more about this next time. Let me not belabor this at the moment. But we did this too. I just didn't tell you this is the general rule. I did this for the example, but there's something more general to say there. We should say that calmly at the start of class next time probably. So you'll be very happy. Everyone here, I think, with a few exceptions possibly, should be very happy what happens on page 41. What happened on page 40 is probably more relevant. So I know some of you are thinking about dropping this class. I get it. Because it's so horrible, I understand. It will get better. It will get better. And part of the reason it's going to get better is this remark 2.38. I admit that I have been developing the course over a normed linear space, right? But classically, the course has been over Rn. And as time has gone on, from the start of the course, I have gotten more and more normed linear space stuff done, right? But there always comes a point in the course where the students will not indulge me further. So I have to stop doing normed linear space stuff and start keeping it real. We have reached that point at page 40. At page 40, we start working in Rn. So past this point, it's Rn all the way, for the most part.
Can't you just order R n by n into an Rn, basically? If you just tear apart the EIJs.
Well, that is what we've done. And you're right, but then we have to, sort through the basis. So I'm not saying we can't do calculus in normed linear space. In fact, I have been. What I'm saying is that you guys will understand this part of the course much more, what we're about to do. Like, so starting on page 41, I define like partial derivative from Rn to Rm. This is in some sense redundant because we already made this definition for a normed linear space of which Rn is one. Right? So, but I want to show you. I can actually draw pictures for the partial derivatives in 2 dimensions, right? This is the meaning geometrically of partial f, partial x, partial f, partial y. You guys know this stuff from Calc 3, hopefully. Here's a brief review of it for you. And here's the deal. So if we've got a function from Rn to Rm, if it's differentiable, then the differential has derivative matrix f prime, and it has components which are expressed in terms of partial derivatives of the component functions. In particular, the ijth component function, ijth component of the differential is the jth partial derivative of the ith component function. In other words, the Jacobian matrix looks like this. You just calculate partial derivatives of the component functions and write them out, simple as. And if you look at this, it's like the x derivative, well, the x1 derivative for the first column, the x2 derivative for the second column, all the way out to the nth derivative for the nth column. If you look at it this way, it's the gradient of the first component function, the gradient of the second component function, the gradient of the nth component function. So you can either look at the Jacobian matrix as a stack of partial derivatives, a concatenation of partial derivatives, or as a stack of gradient vectors, which I'm sure I'll say here in a second. Right, this is what I just said, but typeset. Like this, or like that. And then, if you look further, you'll find out that I have returned back to that example that I told you guys to read and shown that we can reproduce this matrix here by taking partial derivatives that you know and love from calculus 3. Like, this is my function, right? Partial x of that is y. Partial x of that, 2x. Partial x of that, 1. Partial y of that, x. Partial y of that, 0. Partial y of that, 3. And that's the same thing I derived earlier in the notes by looking at the difference quotient and, sorting through the Frechet derivative. But this matrix will give you the best linear approximation to the change in this function at the point. So, anyway, sorry, I know I'm hurrying a little bit today, but it's partly because I don't want to be in this part of the material too long, because I want to get to that part of the material, which you guys will feel better about, I think. So, anyway, that's all I got for today. I'm sorry, I'm ending class early. I'm sorry about that. I'm sorry. Very sorry.
Thanks, Dr.
Yes.